This is K Devender Reddy, Assistant Professor in Institute of Aeronautical Engineering College, Triple Department. In this video, we are going to discuss about torque production in three-phase induction motor. And we'll focus on how the torque will develop in a three-phase induction motor and the relative expressions for torque, that is under starting condition, running condition, and full load condition, as well as we are also discuss maximum torque condition in this video. The torque produced by a three-phase induction motor depends upon generally two factors in the case of a DC motors. One is flux and armature current of the DC motor. But whereas in the case of the AC machines, that is comes under the three-phase AC machine called induction motor, the torque not only depends upon flux and a rotor current, it is also depends on power factor, because three-phase AC supply, in the case of the three-phase AC supply, power factor will play the major role, that is angular velocity between the phases. So here in this case, the torque produced by a three-phase induction motor depends upon magnitude of rotor current, which is circulated in the rotor circuit, and air gap flux, which is responsible for inducing the rotor current, and another factor is power factor. So by combining all these three factors, we'll get the equation torque proportional to flux times of I2 cos phi 2, where flux is responsible for producing the induced EMF, and I2 is a rotor current, and cos phi 2 is the power factor of three-phase induction motor rotor quantities. So generally, we know the flux produced by the stator, it is proportional to E1, and we know the transformation ratio K is defined as ratio of secondary voltage to the primary voltage in the case of the transformer. Similarly, in the case of the induction motor, the transformation ratio constant K equal to secondary voltage E2 by primary voltage E1, that is a stator voltage and rotor voltage respectively. And where K equal to E2 by E1 is the stator voltage is proportional to flux produced, and we can naming it as E2 is equal to phi 2. Rotor current I2 is also defined as under stationary condition, at standstill condition, rotor current I2 equal to E2 rotor induced EMF by impedance of the rotor Z2, which is equal to E2 by square root of R2 square plus X2 square, which is at starting condition. At starting condition, induced current or circulating current in the rotor I2 equal to E2 by Z2, that is impedance of the rotor, which is equal to E2 by square root of R2 square plus X2 square at starting, that is when slip becomes 1 at starting. At starting, slip becomes 1. But under running condition, slip will come into the picture. So I2 equal to slip times of the induced EMF in the rotor divided by impedance of the rotor, that is Z2. So which is equal to slip times of the induced EMF in the rotor divided by square root of R2 square plus slip square times of X2 square, that is inductive reactance of the rotor circuit. So this X2 equal to, generally at starting, this is 2 pi Fr into L, where Fr is nothing but a rotor frequency, which is equal to slip times of the frequency of the stator, S into Fs. So we can write it as X2 equal to 2 pi into S times of the frequency of the supply into inductance of the rotor winding. So when at starting slip becomes 1, X2 equal to 2 pi into Fs into L under starting condition. But at a running condition, so inductive reactance x2 equal to 2 pi into s into slip into frequency of the stator into inductive inductance of the rotor winding, x2 equal to 2 pi s into fs into L. So similarly here, we are writing the expression for induced current or current in the rotor circuit equal to slip times of the induced EMF by impedance. So generally we know the formula for impedance, that is square root of R2 square plus S times of the X2 whole square. Inductive reactance is depending upon the slip factor of the induction motor. So rotor current, we can derive a expression for the rotor current I2 equal to slip times of the induced EMF by impedance of the rotor circuit. And the later part, power factor. Power factor is defined as ratio of resistance, rotor resistance to the impedance of the rotor winding. So which is equal to R2 by Z2, ratio of rotor resistance cos theta 2 equal to ratio of resistance, rotor resistance by impedance of the rotor circuit, which is equal to R2 by R2 square, square root of R2 square plus S times of X2 whole square. So from the above equation, torque equation can be rewritten as torque proportional to, as we discussed, torque is proportional to E2, induced EMF, and so first torque is proportional to what we discussed. Torque is proportional to I2, flux, I2, and power factor cos theta, cos theta. So from this, we can rewritten as torque is proportional to E2, that is E2 is proportional to flux, I2 cos theta, that is torque proportional to product of rotor induced EMF into rotor current into power factor of rotor. So substitute all these three, rotor current, rotor induced EMF as well as the power factor. So torque proportional to E2 and torque proportional to I2, that is I2 equal to S times of the E2 by impedance, square root of impedance of the or magnitude of impedance of the rotor into power factor cos theta 2, that is R2 by magnitude of impedance of the rotor circuit. So simplify this, we'll get torque is proportional to S times of E2 square into R2 by impedance of the rotor winding. So then after, torque is proportional to S times of E2 square into R2 by impedance of the winding, that is square root of R2 square plus S times of X2 whole square. So now we have to write the proportionality constant, that is T equal to some proportionality constant I am naming as K into S times of E2 square into R2 by square root of R2 square plus S times of X2 whole square. So from this proportionality constant, where K equal to 2 pi into Ns by 60. 2 pi into Ns by 60. Sorry, the proportionality constant is 3 by 2 pi Ns, where Ns is in terms of RPS, that is equal to Ns in terms of RPM by 60. So from this, T equal to K is a 3 by 2 pi Ns, 2 pi into synchronous speed Ns by 60 into slip times of E2 square R2 by impedance, magnitude of impedance, that is square root of R2 square plus S times of X2 whole square. So simplify this, we'll get torque equal to 180 by 2 pi Ns, where Ns, capital Ns represent the speed in terms of the RPM, into S times of E2 square R2 by impedance magnitude of rotor, that is R2 square plus S times of X2 whole square. This is the expression for torque under running condition. This is under running condition. At the starting condition, simply S becomes 1, torque slip becomes 1, that is 180 by 2 pi ns, that is the proportionality constant K into E2 square, slip becomes 1, that is 1 R2 by R2 square plus X2 square, impedance of the rotor winding under starting condition or at starting condition. At starting condition. At starting condition, slip becomes 1. Under running condition, slip is means less than 1. That is between, under running condition, in between 0 to 1. Slip is in between 0 to 1. So this is a case of the three-phase induction motor expression for the torque under starting condition as well as the under running condition. Next one, we'll also discuss in this video condition for maximum torque. The starting torque is the torque produced by the induction motor when it is at the starting point. We know that the rotor speed at the time of the starting, that is 0. So slip equal to ns minus the rotor speed I am represented with nr, ns minus nr by ns. It becomes 1, that is slip equal to 1 at starting condition. So the equation of the starting torque is easily obtained by simply putting the value of s equal to 1 in the previous expression. We already derived that expression, torque equal to k times, that is a proportionality constant, into E2 square R2 by square root of R2 square plus X2 square whole square, that is R2 square by R2 square plus X2 square. The rotor resistance, rotor inductive reactance, and the synchronous speed of induction motor remains constant. To derive the condition for maximum torque, first of all, we need to know the constant parameters and variable parameters in the expression. So in the expression, the supply voltage to the three-phase induction motor usually a rated voltage and it remains constant, and the stator EMF also remains constant, and the transformation ratio of the rotor transformation ratio of rotor EMF to the stator EMF, and if stator EMF remains constant, then rotor EMF also remains constant, so your transformation ratio is also constant. If you want to find the maximum value of any quantity, then we have to differentiate that quantity concerning some of the variable parameter and then put it into equal to 0. In this case, in the maximum torque expression case, we need to derive the condition for maximum torque so that we differentiate the maximum torque expression with respect to the variable quantity, that is in the expression variable quantity is a slip. So that is why I am differentiating the torque expression with respect to the slip, that is dt by ds, and equate it to 0. Differentiate the torque expression with respect to the variable quantity, that is a slip, and equate it to 0. So we have a torque expression under running condition. This is under running condition. Torque under running condition equal to some proportionality constant K into slip times of the induced EMF in the rotor square into R2 by R2 square plus S times of the X2 whole square. So generally, the simplified equivalent diagram for the rotor, that is rotor resistance as well as the rotor inductive reactance and the rotor induced EMF, that is S times of the induced EMF of the rotor under running condition, and a rotor resistance R2, and it is a variable one, and inductive reactance of the rotor is X2. This is rotor induced EMF, S times of the induced EMF. So differentiate that expression d by ds of proportionality constant K into S times of the E2 square into R2 by R2 square plus X2 square S square. Differentiate it and equate it to 0. So by differentiating this expression, we will get R2 equal to slip times of the X2. Differentiate the above expression and equate it to 0, we will get R2 equal to slip times of the X2. In another way also, we derive the expression for maximum torque condition, that is torque equal to some proportionality constant K into S times of the E2 square R2 by R2 square plus S square times of the X2 square. So from this, we are taking another constant, that is a K1 equal to K times of the E2 square. I am making another constant which is equal to some K1 into S times of the R2 by R2 square plus S square times of X2 square. X2. That is X2 square. Then K1 into slip times of the R2 by S whole square plus X2 square, making a S as a common, and slip becomes cancelled, and T equal to some proportionality constant, another proportionality constant K1 into R2 by S whole square plus X2 square. So need some simplification for this. Some K1 into R2. Let's simplify the denominator, that is R2 by root S plus X2 into square root S, and making whole square, and it is K times of the R2 divided by R2 by root S plus X2 times of the square root S into R2 by square root S minus X2 into square root S. Then after, so for this expression from equation, we make it as equation number 1. So denominator of the equation number 1, T becomes T maximum when denominator make it as 0. So R2 by square root S plus X2 times of the square root S into R2 by square root S minus X2 square root S, make it as equal to 0. Simplify this, R2 square by S plus R2 X2, sorry it is minus, in this case T maximum becomes when denominator equal to 0, that is R2 by square root S plus square root times of S into X2 into R2 by square root S minus square root times of S into X2. So simplify this and make it as equal to 0. R2 into R2 by square root S, that is R2 by S, minus R2 X2 plus R2 X2 minus S times of X2 square, that is equal to 0. These are the cancelled now. This is also X2. R2 by R2 into R2, this is R2 square, this is X2 square, R2 square by S minus S times of the X2 square. So R2 square is equal to S times of the X2 square. This is S square. So now R2 equal to S times of the X2. This is another way to derive the expression for torque maximum. So similarly, this is a slip corresponding to the maximum torque, that is S maximum equal to R2 by X2. Simply substitute this value in the torque expression, we will get T maximum, torque maximum expression. T becomes T maximum when slip maximum equal to R2 by X2, or else when R2 equal to S times of the X2. So generally we have some proportionality constant K into S times of E2 square into R2. So I am replacing now R2 by either Sx2 or else Sx2 by R2. So I am making as Sx2 by R2, that is K times of S times of E2 square by R2 divided by R2 square plus S times of X2 replaced with R2 square. So it is K times of T maximum equal to K times of SE2 square into R2 by 2R2 square. So square cancel here and we get K times of S into E2 square by 2R2. It is the expression for T maximum. Or else you can also derive the expression in a similar way. Instead of substituting Sx2 by R2, you can also substitute R2 by Sx2. We'll get the expression T maximum equal to K times of S into E2 square into, here R2 can replace with Sx2, S times of the X2 divided by R2 can be replaced with Sx2. So it is S square X2 square plus S square X2 square. So we have K times of S square E2 square X2 by 2S square times of X2 square. Here square and X2 cancel and S square and S square cancel. We'll get K times of E2 square by 2X2. It is another expression for maximum torque. When you substitute R2 by S times of the X2, we'll get in another expression that is called maximum torque expression. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.